Good afternoon, sir. Sir, hello.
हेलो, हाँ बोलो।
सर एक्चुअली लेटरल एंट्री से एक नया स्टूडेंट आया है, मनोज कुमार।
ठीक है।
तो सर आई गेस सर उसका थोड़ा मिस हुआ होगा, बट वो लेटरल एंट्री से सर, तो उसका रोल नंबर कहाँ शिफ्ट होगा, बीच में या फिर लास्ट में?
उन्हीं के तो अलग रोल नंबर सीरीज होती है, 501 502 ऐसे चलती है इनकी रोल नंबर सीरीज।
ओके सर।
है ना, उनका रोल नंबर मिलेगा, वो लास्ट में मिलेगा, उसका होगा 2K21CH501।
ओके सर।
उसको बोल रजिस्ट्रेशन कर लेगा अभी, है ना, सब्जेक्ट रजिस्ट्रेशन करने होंगे उनको।
ओके सर।
बाकी स्टूडेंट्स थोड़े जल्दी ज्वाइन करें, देन वी विल स्टार्ट 18 19। ठीक है, स्टार्ट करते हैं, मतलब बाकी स्टूडेंट्स ज्वाइन होते रहेंगे।
यस सर।
तो today we will start the transport phenomena. First part of the transport phenomena, that is the momentum transport. Okay, so there are three types of transport which we will study in this subject. First is the momentum transport, second is the heat transport, third is the mass transport. So this is the first part, momentum transport. Okay. So first you have to today I will give you I will teach you the basic definitions of the some terms. Okay. So basically momentum transport deals with the flow, deals with the physics of fluid. Okay, so it is basically the transportation of fluid. When you say the momentum transport, here we are not dealing with the solid material, because in the chemical engineering most of the chemicals which we will use, they are in the fluid form. Okay, not the solid form. In the solid material also transported in the as a fluid, and by we convert the solid particle in the solid material in the particles, and that particle can be transported as a fluid. Okay, so here we will study the momentum transport, which is also called the fluid mechanics. Okay. So momentum transport is nothing but the fluid mechanics. This is the generalized form of fluid mechanics. You know, in fluid mechanics, generally when you study the fluid mechanics in civil engineering or the mechanical engineering, they will study the fluid mechanics of either water or steam or oil. Okay, here we will consider all chemicals. You know, so in the chemical engineering, the momentum transport is more generalized part. Okay, so in the momentum transport, the here we have to deal with the fluid. So first we have to define the fluid. What is the fluid? How you define the fluid phase? How you define the fluid? What is the fluid?
Sir,
Anyone?
anything that occupies a particular space where the atoms are closely packed.
No, that is not the definition of fluid. Fluid means the any material which can flow. That is the fluid. Okay. So basic definition of fluid is any material which can flow. If any material cannot flow, then it is not a fluid. Which can be. Okay, that is the fluid. By that word you can understand. Fluid means it can be flow. Okay. Now there are two different types of fluid. First is the compressible fluid. Second is the incompressible fluid. So what is the compressible fluid? Compressible fluids are the fluids where the density of material can be changed with changing of pressure. So you can change the density of material with change of the pressure. That is the compressible fluid. Okay. And incompressible fluid, when the density of the material cannot change with change of the pressure. That is the incompressible fluid. And rho or density is the function of pressure. And incompressible fluid, when density is not the function of pressure. When density cannot change with changing pressure. So generally liquids are incompressible fluids and gases are compressible fluids. Okay. So you have the compressible and incompressible fluids. Now what is the definition of pressure? Second term which comes as a pressure. Here you understand the fluid. So fluid includes the gases also, fluid includes the liquid also. Both are the fluids, both can be fluid. Okay. It depends upon both are the different phases. Liquid has the different phase, gas has the different phase, but both are the fluids. Okay. Now fluids can be compressible or incompressible. Generally, liquids are incompressible, gases are compressible. But there are conditions when you have the incompressible liquids also. There are some type of liquids which are also compressible. Okay. Otherwise, liquids are not compressible. Okay. Now, pressure or hydraulic pressure. What is the definition of hydraulic pressure? Anyone? What is the pressure? In physics, how you define the pressure?
Uh, Sir, can you repeat?
What is the pressure? What is the definition of pressure?
Sir, the amount of force exerted on a specified area.
Yes, है ना? So this is the force per unit area. That is the pressure. Okay. Now tell me, pressure is a vector quantity, tensor quantity, or a scalar quantity? It is a vector quantity, scalar quantity, or the second order tensor quantity.
Sir, second.
Yes, है ना? By definition, pressure is a second order tensor quantity. Okay. Why it is a second order tensor quantity? Because F force is a vector quantity, force have a direction, and area is also a vector quantity. And area represented the surface. Suppose this is a surface, so this surface A has a direction. So you can say the outward normal direction represent the direction of the surface. Okay. Now you might apply the force in this direction or in this direction or in this direction. Okay, so based on that, suppose the direction of force is J, direction of surface is I, so you have the pressure Ji. So pressure is a second order tensor quantity. Okay, now this statement that pressure is a second order tensor quantity is true when you are dealing with the solid material. Okay, when you are calculating the pressure in the solid material. So suppose you have a surface and you are using a hammer to pressurize put the force on the surface. So you can measure the pressure exerted by the hammer on the surface. So that is the example of the solid mechanics, how the pressure works in the solid material mechanics. There you have to calculate the pressure. There you have to consider pressure as a second order tensor. But in the fluid mechanics, pressure is a scalar quantity. So hydraulic pressure, hydraulic means fluid pressure, है ना? So hydraulic pressure is a scalar quantity. Why I am telling you? Okay. In fluid mechanics, hydraulic pressure is a scalar quantity. Okay, why it is a scalar quantity? Because suppose this is a closed container, where you have the fluid. So there are fluid particles. There is a fluid filled inside the closed container. Okay. Now you assume a surface here, a microscopic surface at this point. Okay. Now if you take the surface, so how the hydraulic pressure works? For that you have to understand how the hydraulic pressure, why the fluid exert any force on the surface. How it is work? When you take the fluid means the material which can flow. So it is either the liquid or the gas. Suppose this is a surface and you have a fluid is present, this surface is present inside a fluid. So what will happen? The molecules of fluid that will move. This is the difference between the solid phase, liquid phase, and gaseous phase. In the liquid and gaseous phase, molecules can move. Okay, so that molecules will move that have any kinetic energy, and when these molecules collide with the surface, solid surface, then they will exert a force on the surface. Okay, so the moving molecules, when they collide at a surface, they will exert the force on the surface, and that force is per unit force force per unit area is called the hydraulic pressure. So what is the definition of hydraulic pressure? The force exerted by molecules of fluid on a given surface. Okay, now suppose if you check the position, okay, because the movement of the molecules inside the fluid as well as in the gas, that is the random. Fluid, the inside the liquid or inside the gas, the molecules, the gas molecule or liquid molecules will not move in a given direction. They move in the random way. Okay, so when you measure the force exerted at each direction, you will find at each direction, suppose this is a point, so force exerted by molecules in this direction, force exerted by a molecule in this direction, force exerted by a molecule in this direction, in all directions you have the same force. Okay, suppose this is a microscopic cube. Suppose you have a microscopic cube inside a fluid. This is a cubical structure. Suppose it is a microscopic cube which is present inside a fluid. So you have the 6 different surface in the cube, 1, 2, 3, 4, 5, 6, which are present in the 3 different direction. And 3 different directions. So this surface has the direction this surface also has the direction this. Here upper surface has this direction, lower surface also has this direction, and this surface has the front surface has this direction. So you have the 3 different 6 surfaces which are present in the 3 different directions. Now suppose this cube has very small dimension. This is delta x, delta y, delta z. Well, delta x, delta y, delta z is tends to 0. And delta x equal to delta y equal to delta z, that is tends to 0. Okay, so this is our assumption, and this is basically a point. Now at the molecule which collide at this surface, the molecules which collide at this, so you will find that at all surfaces you have the same amount of force, and the direction of force is random. In each direction you have the same amount of force. Okay, and every surface you have the same amount of force. So no matter when you write the second order tensor, and pressure, when you make the pressure as a second order tensor, it has the 9 components. Second order tensor has the 9 components. PII or P1 to 3, we will write 1 to 3. That is much easier to understand, or XYZ. So we start the XX, PXX, PXY, PXZ, PYX, PYY, PYZ, PZX, PZY, PZZ. These are the 9 components of the pressure tensor. So in the hydraulic pressure, when you talking about the hydraulic pressure, so at each surface you have the same amount of force, and at each surface, at each direction, you have the same amount of force. Okay, so these all components are equal to each other. Okay, so these all components are equal to each other. That means these components will not depend upon the direction. That means these components will not depend upon the direction. Okay, that means you need not to worry about the direction. Okay, you need not to worry that it is a PXX or PXY or PXZ, because in all directions, in all surface, you have the same force, which shows that it is a scalar quantity. When the value of the pressure is not dependent upon, if the value of pressure is not depending upon the direction, that means it is a scalar quantity. You need not to write the 9 component, you have to write a 1 component only. Okay, so it is a scalar quantity. Now you understand why the hydraulic pressure is a scalar quantity, although it is a, by definition, it is a second order tensor, but because the all forces are equal in all direction, and the all surfaces, the forces exerted at each surface is also equal, so you have the all components in the second order tensor are equal, and you are that results the scalar quantity. Okay, this is the definition of second order. This is the definition of pressure. Okay, now one more important thing, density. How you define the density? It is the most common physical property of fluid. What is the density, or what is the density? What is the definition of density? Anyone? What is the definition
Mass
of
per
density?
unit volume.
Mass per unit volume. So generally density is the function of temperature for incompressible fluid, and it is the function of temperature as well as pressure for compressible fluid. This is very important in the transport phenomena. It is an incompressible fluid or compressible fluid, because density is a basic property of the fluid. Pressure, density, temperature you already studied in the thermodynamics. Okay, that the definition of temperature. Now, because we are studying about the fluid, you should know some basic definition of the flow. How to define the flow? So, how to define the flow? First is the velocity. What is the definition of velocity?
So displacement per unit time.
Yes, displacement per unit time. So it is a vector quantity. It is a vector quantity. Now in fluid mechanics, you have the different type of velocities. Okay. So first is the linear velocity. It is also called the local velocity. Okay. Suppose you have a pipeline and fluid is flowing inside the pipeline. Okay. So what will happen? Because here you have the solid surface. In the solid surface, you have a friction. एक मिनट रुको. Am I audible?
Yes, sir.
So there are different types of velocity in the fluid mechanics. So one is the linear velocity. It is also called the local velocity. So local velocity is basically, suppose a fluid is flowing inside a pipeline. Okay. So what will happen? The velocity of the fluid is not same at each point. Okay. At the boundaries, at the solid liquid interface, where you have the pipe and liquid boundary, where you have a friction force. Solid friction, है ना? Solid material exerted, solid surface exerted the friction on the fluid. Okay. That's why the velocity at this point is zero. At the solid liquid interface, velocity of the fluid is zero. Okay. At the middle of the point, velocity is highest. At the middle of the pipeline, you have the highest velocity, Vmax. Okay. So if you are measuring the velocity at a given point, and suppose you are measuring the velocity from the distance r, of the interface. Okay. Then you are measuring the velocity v at z equal to r. Okay, so this is the linear velocity. Okay, the velocity at a given point is called the linear velocity. Okay, now second type of velocity is, which is more useful, that is the average velocity. So what is the average velocity? You have to, because here the velocity is zero, at the middle point you have the highest velocity. When you average out the velocity value, you will get the average velocity. Is 0 to maximum value. Okay, when you average it out, you will get the average velocity. Okay, so these are the two different type of velocity used in the fluid mechanics. Now there are other terms also which is used to define the flow. Okay, so first is the volumetric flow rate. So this is the velocity. After this you have the second term, that is the volumetric flow rate. Okay, volumetric flow rate represented by Q. Okay, so basically suppose you have a pipeline, fluid is flowing inside the pipeline. So, and you are collecting the fluid after the pipeline, you are collecting the fluid in a measuring flask. Okay, so you have to collect at a given time how much fluid is collected. Suppose the 2 liter fluid is collected in 1 minute. Okay, in 1 minute you have collected the 2 liter fluid. Means the 2 liter fluid is flowing in a 1 minute inside the pipeline. So the volumetric flow rate is 2 liter per minute. Or you can write 0.002 divided by 60 meter cube per second. Okay, so this is the volumetric flow rate. How much volume is flowing per unit time? Okay, so volumetric flow rate depends upon the cross-sectional area, diameter of the pipe. If the diameter is large, then you have the higher volumetric flow rate. If the diameter is less, you have the lesser volumetric flow rate. Okay, you can calculate the average velocity from the volumetric flow rate. Suppose cross-sectional area of pipe is capital A and diameter is capital R. Capital D, diameter is capital T. So you can write the average velocity, then you can write average velocity of fluid V average, that is equal to Q divided by A. Volumetric flow rate divided by the cross-sectional area, or that can also written as Q divided by pi by 4 d square. Cross-sectional area equal to pi by 4 d square. It is a circular. In the tubes, you have the circular tube only. Tube pipelines are the circular shape only. So you have the pi by 4 d square. This is the cross-sectional area. So this is how you can convert the volumetric flow rate to the average velocity. Or similarly, you can also calculate the volumetric flow rate if you know the average velocity. Okay. Third term which is used is the mass flow rate. So mass flow rate is kg of fluid or gram of fluid flows per unit second. Okay, so how much amount of fluid in terms of mass is flowing per unit second. So how you can calculate the mass flow rate? How you convert the mass flow rate to the volumetric flow rate? So mass flow rate is represented by the m dot. Okay, mass flow rate is generally represented by the m dot. Okay, so m dot equal to Q divided by rho. Rho is the meter cube per kg density. So the unit, here you have the unit, the meter cube per second. Here you have the unit meter cube per kg. When you divide both, you will get kg per second. Okay. So you can convert mass flow rate equal to Q divided by rho, or you can also write m dot equal to Q divided by rho, that is equal to, if it is the flow rate, fluid is flowing inside the tube, you can write V average divided by A, area of the cross-sectional area of the tube, multiplied by rho, or you can write V average divided by pi by 4 T square rho. ठीक है? Okay, okay, so in this way, these are the three important flow properties, है ना, which characterize the flow. So velocities, in the velocity you have the linear velocity or the local velocity as well as the average velocity. Then you have the volumetric flow rate, okay, which is the meter cube per second or liter per minute or liter per second, है ना, how much volume of the fluid flowing per unit time. Then you have the mass flow rate. Okay, mass flow rate is how much kg of fluid flowing per unit time. Okay, you can also represent the molar flow rate, but molar flow rate is not used in the fluid mechanics. So I will tell you the reason, है ना, when we will study the fluid mechanics, then I will in the detail, then I will tell you in the momentum transport only, in this unit, in this subject only, I will tell you why we are not using moles, है ना, in this in the fluid mechanics, है ना, why we are not using moles in the fluid mechanics. We use the moles in the mass transfer, है ना, but not in the fluid mechanics. Fluid mechanics generally we use more mass only, not the moles. Okay. Now there are some basic assumptions or some basic properties of the momentum transport. Okay. So first I will define the momentum transport, why it is called the momentum transport. Definition of momentum transport. So momentum transport deals with the transport of momentum. Deals with the transport of momentum. Which is responsible for flow of fluid. This is responsible for flow of fluid. So you can ask why we use the momentum transport especially for the fluid mechanics. Why the transportation of momentum is important in the fluid. Basically, if you imagine the fluid mechanics, it looks like it is the transportation of material. Enough when the liquid is flowing inside a pipeline, basically it is a transportation of material. But why we are writing it is a momentum transport? Because transportation of material occurs due to the transportation of force. Okay, transportation of momentum. So you can make an analogy of the fluid mechanics with the solid materials. Okay, so if you make the analogy with fluid mechanics with the solid mechanics, applied mechanics or the solid mechanics, then the principle of momentum transport is similar to the Newton's law of mechanics, and the Newton's three laws of mechanics. That is the second law of Newton's second law. What is the Newton's first law and second law? Anyone? What is the Newton's first law?
Sir, energy is conserved.
First law is energy.
That's the thermodynamics.
है ना, the first law and the Newton's second law.
Sir, momentum is conserved.
momentum is conserved. That is the Newton's second law. And third law,
Every action has an opposite, equal and opposite reaction.
reaction. Okay, so basically, when you apply this law on the fluid, that will become the momentum transport. Okay, so similar as you have written that the first law, Newton's first law, is that the energy is conserved. When you write the same law for the momentum transport, you have a law that tells you that mass is conserved. Mass cannot be created, cannot be destroyed. Okay. Second law, momentum is conserved. That is same in the fluid mechanics. In fluid mechanics also, we will use the momentum is conserved. So when you write the momentum is conserved in the solid mechanics, you will get the F equal to ma, force equal to F equal to ma equation. Here you will get the mass equation of motion that I will teach you in this momentum transport part. The equation of motion, which is used to predict the flow properties of any fluid. Okay. Now, third law, every action has a reaction, that is also used in the fluid mechanics. Okay, so basically that is the same thing. Okay, so momentum transport, because it is the transportation of momentum. And when though in the solid mechanics, you have already studied how the momentum is when the two bodies collide, which both are moving at different velocity, or one is stationary condition, one is moving at a different velocity. So there is a transportation of force, and when the more transportation of momentum, and the momentum, when the momentum transport happens, then the material will move. Okay, so the movement of material depend upon the transportation of momentum. Okay, that's why it is called the momentum transport. Fluid mechanics is called the momentum transport. Okay, now there are some basic assumption in the fluid mechanics or the momentum transport. Okay, we will study fluid mechanics in separate subject also. Okay, in when you study the fluid mechanics subject in next semester, you will study the fluid mechanics subject in the next semester. There we will study about the pumps. There are different type of equipments used in the fluid mechanics. Okay, here we will derive the expression. We will in the transport phenomena, we will derive different type of mathematical models which is used in the fluid mechanics. You know, how to calculate the velocity inside a tube, how to calculate the volumetric flow rate of the tube, that we will calculate in this subject. Okay, so so first is the no slip boundary condition. First assumption which is used in the fluid mechanics, that is in the momentum transport in this subject, that is the no slip boundary condition. So what is the no slip boundary condition? Suppose you have a solid surface. This is a solid surface. Okay, fluid is flowing on the solid surface. Okay, so the layer of fluid which comes with the contact of the layer of liquid or fluid which comes in the contact of the solid material, the velocity of that layer is zero, or the velocity of that layer is equal to the velocity of the solid layer. Okay, if the solid layer is moving, then that layer also has the same velocity. If the solid layer is moving with the velocity v, then the exerted layer of the solid material surface, that has the same velocity v. Okay, that is called the no slip boundary condition. That means there is a no slip between the solid body and the liquid interface, at the solid liquid interface. So we can write that whenever a fluid comes to contact whenever a fluid comes in contact with any solid boundary the adjacent layer of the fluid is fluid in contact with the solid surface in contact with solid surface which has the same velocity as the solid surface. So this is the most common assumption in the fluid mechanics. And this is widely used also. Whenever you have to calculate the velocity, because all the friction, all the resistance come for the solid surface. Generally in the chemical engineering and even the other subjects also, the fluid flows with the solid, within contact with the solid material, and all the resistance on the fluid comes from the solid material only, due to the friction of the solid material. Okay, so it is so this assumption is very important, and then only you can calculate the the pressure drop or the velocity of the fluid or the flow rate of the fluid inside a given channel. Okay, one more thing which you should know, before going to the next topic, one more thing you should know, that the when we studied the fluid mechanics, generally we assume that fluid flows in the layers. Okay, fluid flows in the layers. Okay, like that layer might be interchange also. Sometimes that layer there is a mixing between the layers also. Sometimes there is a no mixing between the layers. But we assume that fluid flows in the layers only. Okay, one above other. Okay, there might be some mixing in between these layers, among the layers, or there might not any mixing in different layers. Okay, among these layers, but the fluid always flows in the layers. Even the liquid, it is also true for the liquid. It is also true for the gas. So this is also very basic assumption which is used to solve the problem. Okay, so first assumption is no slip boundary condition. So there is a no slip between the solid material as solid surface and the liquid surface at the solid liquid interface. If the solid surface is a stationary condition, the velocity of solid surface is 0, then the velocity of the liquid surface which comes in the contact in that solid surface, that is also 0. If surface is moving with any given velocity, then the liquid comes to the contact of that solid surface that also moving with the same velocity. And if it is moving with the velocity v, the liquid will also move with the velocity v. Okay, then you have to understand that the fluid always flow in the layers. Okay, one above other. Okay, there might be some mixing in between the layers, and there might not any mixing in between the layers. And both conditions are true, but fluid flows in the layer. Okay, so I think this is enough for today's class. Now we will meet on Monday.
Yes sir.
Okay? चलो, any
Okay sir,
confusion?
thank you sir.
आज का तो समझ में आ रहा है इजी. आज का तो आज से मोमेंटम ट्रांसपोर्ट स्टार्ट हो गया है ना. वी हैव कंप्लीटेड द मैथमेटिकल पार्ट. नाउ वी विल स्टार्ट द फिजिक्स.
Yes sir.
Yes, sir.
Excuse me, sir.
हाँ बोलो.
Sir, we are getting an off for 3 days now, so can you please share the recordings of the classes so we
I
can
will.
probably leave?
I will share today only. I will share the recordings also as well as the notes also. And I have already shared the notes printed notes
Yes,
with
sir.
you.
Yes, sir.
You have.
Notes are there. Yes.
I will share the recording.
Okay, sir. Thank you.